Hey, it's Mr. Shrum, and I'm getting some questions about the unit activities and course activities in some of these units. And the month of November, that is when we're starting our Unit 3 microscopic forces and macroscopic function. So we're learning about ionic compounds and metals, covalent compounds, complex structures, and then the unit activity for this unit is called chemical bonding. And in this lesson activity, we're going to classify compounds according to the elements they contain, and then we're going to write the appropriate name and formula for each compound. So if you look around you at this very moment, everything around you is made of atoms. The computer screen you're looking at, the microphone I am talking into right now, yourself, your hands, your body, the room you're sitting in, the food you may be consuming, all of it made of atoms. And these tiny little atoms bond in different ways to form different compounds. So look at the picture to the right here. This is a bowl of salad. The plastic bowl is made of a non-metal. Plastic is a covalent compound that consists of atoms bonded together to form long chains. The steel fork used to eat the salad is made from a combination of metals. So we have a non-metal bowl and a combination of metals in the fork. The salt sprinkled on the salad for flavoring is an ionic compound. Vinegar, which people sometimes add to salads, contains acetate, and that is a polyatomic ion. The salad itself is made from veggies that are often grown using fertilizers such as urea. Urea is an organic compound consisting of atoms of carbon covalently bonded to oxygen and nitrogen. So we got the oxygen and the nitrogen and carbon. And if we look at these compounds, a covalent compound consists of atoms connected by covalent bonds. Ionic compound consists of positive and negative ions. Polyatomic ion, a covalently bonded group of atoms that has a positive or negative charge. So it's an ion with more than one atom in the ion. And then organic compound, anything that contains carbon, with exceptions including carbonates and carbon oxides. So in this activity, you'll classify compounds and write the correct names and formulas of different ionic, covalent, polyatomic ion, and organic compounds. Before you begin, let's review some of the properties, applications, and Lewis structures for these types of compounds. Here you see the ionic compound explanation. That is when a metal atom bonds with a non-metal atom. And here we have sodium, that is a metal. Chlorine is on the other side of the element table, the periodic table. Therefore, when they combine, they form an ionic compound. Electrons are transferred from one atom to another. In this transference of electrons, when things transfer electrons, they form ions. Salt is a common example of an ionic compound. The charge on the ions of most elements in the main group can be predicted from the periodic table. For the ions of transition metals, the charge must be specified in the name of the compound. So sometimes it's not as easy to tell right off the bat. Covalent compounds form by sharing electrons between two non-metal atoms. The sharing of electrons results in the atoms achieving a stable electronic configuration. An example of a covalent compound is carbon dioxide gas, which is commonly used in fire extinguishers. Polyatomic ions, ionic compounds, also form when a polyatomic ion bonds with another ion. A polyatomic ion is one in which multiple atoms are joined together by covalent bonds, but have a net charge. For example, two polyatomic nitrate ions bond with a calcium ion. See the calcium ion here, and then the two nitrates right here. And they form calcium nitrate. And this is written as Ca, and then you put these parentheses, NO3, outer parentheses 2. Calcium nitrate is used as a component in fertilizers. Organic compounds are carbon-based compounds. Carbon atoms form covalent bonds with each other and with hydrogen. The simplest type of organic compounds are hydrocarbons. They contain a chain of carbon atoms surrounded by hydrogen. So here is an example, hexane. And in this activity, this is the scoring I will be using. So go over that before and make sure you hit all of those points. Ionic and covalent compounds. Part A, find the positions of the elements magnesium and fluorine, and then answer the following questions. So we'll open up the table. Looking for a magnesium. It's right here. It's in the second group. This is the alkaline earth metals. So magnesium is in fact a reactive metal. And fluorine is on the other side of the table. Oh, my bad. There we go. Group 17, the halogens. This is a group of highly reactive non-metals. So we have magnesium, a reactive metal, and fluorine, a reactive non-metal. And there we go. Magnesium is a metal, and it has 2 valence electrons. And a way to easily predict that is group 1 has 1 valence, group 2 has 2 valence, group so we have group 1, they have 1 valence electron, 2, then boron would have 3, carbon would have 4, nitrogen 5, oxygen 6, 7, 8. So if you go by the group numbers, at least for the ones, and ignore the transition metals here, that will tell you how many valence electrons it has on the outside. So 1, 2, 3, 4, 5, 6, 7, 8. Magnesium is in group 2. It has 2 valence electrons. Fluorine is a non-metal, and it is in group 17, so it has 7 valence electrons. Will magnesium and fluorine atoms most likely form an ionic bond or a covalent bond? Well, they will more than likely form an ionic bond. And this is predicted really anytime you have a metal and non-metal reacting from these sides of the table, that will be ionic. Write the name and formula of the compound made of magnesium fluoride. Well, this is pretty easy. It's just called magnesium fluoride. Fluorine changes to IDE, fluoride. And the chemical formula is MgF2 with a subscript 2. Part B, we're looking at sulfur and oxygen. And then we're going to answer the following questions. I'll show you where sulfur and oxygen are. Oops. Here. There we go. Sulfur is right here, group 16. And oxygen is right above it. They're both nonmetals, and they both have 6 valence electrons. Will sulfur and oxygen atoms most likely form an ionic bond or a covalent bond? Well, given their position in the periodic table, they will more than likely form a covalent bond since they're from the same group and same side of the periodic table. A known compound contains 2 atoms of sulfur and 2 atoms of oxygen. Write the name and formula of this compound. Well, this would be called disulfur dioxide because there are 2 atoms of sulfur and 2 atoms of oxygen. Di means 2. So we have to insert that di before the names. Disulfur and then dioxide. Remember IDE. And we would write that as S2O2. Now we are drawing the Lewis structure of the molecule. And that will look like this. Remember, these bonds signify that they are sharing an electron. And this means there are 2 electrons being shared. Part C, find the element carbon and hydrogen on the periodic table and then answer the following questions. Is carbon a metal or a non-metal? Carbon is non-metal and it has 4 valence electrons. Hydrogen is a non-metal. An atom of hydrogen has only 1 valence electrons. Will carbon and hydrogen atoms most likely form an ionic bond or a covalent bond? Well, they are both nonmetals and they will more than likely form a covalent bond. And now we're drawing the skeletal structures of 2 different molecules that are made of 5 carbon atoms and 12 hydrogen ones. So we have C, H3, or CH, or HC, H3C, CH3, CH3. So either ones would work, and you may find another way to write that out in your own way. Name the 2 molecules you drew in question 4. So the one with 5 carbon atoms is called pentane. Pent means 5. The molecule with 4 carbon atoms in the parent chain and 1 attached methyl group is called methylbutane. And if you look that up, It's called isopentane, also called methylbutane. And that is a branched chain saturated hydrocarbon. So hydro means hydrogen and carbon together. Complete the table by writing the name or formula of each compound and the type of bonding that it uses. You may refer to this list of polyatomic ions. So you can click on this, look at the chemical formula, chemical names, and then use that to answer these. So this one would be 2 sulfur atoms and 10 fluorine. So you would do disulfur decafluoride. Calcium sulfide, that would just be calcium sulfide. Nitrogen monoxide, dinitrogen, that's N2. Monoxide just means 1 oxide. There, wait. Let me do this correctly. There we go. Why was this so hard? Okay. Copper 2 hydroxide. So that would be Cu, because why not? And then hydroxide is a hydrogen and oxygen together. So we have OH. And then we'll put in that 2. And then barium sulfate. Barium. And then butane. Butane is just carbon subscript 4, H10. And oh, you can see the rest here. We have diphosphorus tetraiodide for the 3rd one. And then we have aluminum chloride for the 5th one. And then it shows you the types of bonding. So if there are 2 nonmetals, you're going to get covalent bonding. If it's a metal and a nonmetal, ionic. And sometimes you'll have both, as is the case in copper 2 hydroxide and barium sulfate. So you get both. And that's the unit activity. Let's see if we can look at the course activity. Comparing forces between particles. We're going to compare the strengths of the forces between particles of different substances based on a macroscopic property. Properties. Atoms can join with one another to form molecules. In a molecule, 2 or more atoms share their valence electrons through covalent bonding. For example, hydrogen and oxygen atoms combine covalently to form a water molecule H2O, 2 hydrogen plus 1 oxygen. And they share 1 valence electron each with the oxygen atom. However, atoms in a molecule don't always share their electrons evenly. one of the atoms might attract the shared electrons more strongly than the other atom. The side of the molecule to which electrons are pulled more strongly acquires a slight negative charge, while the other side acquires a slight positive charge. This uneven attraction results in a polar molecule. When atoms share electrons evenly in a molecule, the molecule is called a nonpolar molecule. In an ionic compound such as salt, the positive and negative ions are held together by strong forces of attraction, arising from the oppositely charged particles. Most ionic compounds are solids at room temperature because of these strong bonds. In covalent compounds, however, the molecules don't have any net charge, so the particles aren't attracted to each other as strongly. There are forces that can hold the molecules to each other, but they aren't as strong as the forces in ionic compounds. So molecular compounds can exist as solids such as sugar or as liquids such as water at room temperature. Understanding the strengths of molecular bonds has many practical applications. In this activity, you'll determine the relationship between the type of bond in a substance and the strength of the forces between particles. Here's the scoring. For task 1, water and oil drop shapes, sugar, salt, and oil melting points for task 2. So task 1 is looking at the strength of the forces between molecules of a substance and how it affects the substance's macroscopic properties. So what is happening at the very small molecular level is reflected in how it behaves at the large scale where we can see. In this task, you'll examine the shapes of drops of oil and water to learn about the forces that hold the molecules together in these two compounds. You'll need these materials: water, cooking oil, waxed paper, a flat glass surface. So, for example, a mirror, glass baking dish, or a glass coffee table, if you have any of those, a pipette. You could also use an eyedropper. Part A, tear off a small flat sheet of waxed paper. Use the pipette to dispense a drop of water on the waxed paper. Now dry the pipette and use it to dispense a drop of oil on the waxed paper next to the water drop. Be sure the two drops are not touching. Compare and describe the appearance of both drops. The drop of water should appear rounder and taller than the drop of oil. Water should be almost in the shape of a ball. The drop of oil is flatter and generally more spread out on the waxed paper. The shapes of the drops relate to the attractive forces between molecules in a compound. Based on their shapes, how does the attractive force between the water molecules compare with the attractive force between the oil molecules? The water drop is rounder and taller than the oil drop, indicating that it holds together well. So the attractive force between the water molecules is stronger than the attractive force between the oil molecules. And the weaker forces in the oil molecules allow them to spread out more than the water. Water is made of polar molecules and oil is made of nonpolar molecules. Based on your observations, which molecules attract each other more strongly? Polar molecules or nonpolar molecules? It seems that the polar molecules attract each other more strongly than the nonpolar molecules. This difference is evident because water molecules seem to attract each other more strongly than oil molecules based on the shapes of the drops. Using a pipette, dispense a drop of water on a level glass surface. Compare the shape of this drop with the shape of the water drop on the waxed paper. The drop of water on the glass surface is shorter and more spread out than the drop of water on the waxed paper. How does the attractive force between water and wax compare to the attractive force between water and glass? The water drop on the glass surface is shorter and more spread out. This difference indicates that the water molecules are more attracted to glass than they are to wax. Wax is a non-polar substance, but the surface of a piece of glass is polar. Based on part E, which substance is water more attracted to? Polar substances or non-polar substances? Does this finding agree with your observations from part C? Water must be attracted more strongly to polar substances like glass than to non-polar substances like wax. This finding agrees with the observations from part C that the forces between polar molecules are stronger than those between non-polar molecules. Molecules in a gas don't stick together, so they can't form drops as a liquid does. How can you compare the two different gases to determine which gas particles are more strongly attracted to each other? Well, a substance condenses from a gas into a liquid when its particles begin to stick together. The particles are more likely to stick together at lower temperatures. So one method is to cool the two gases to see which one condenses into a liquid first. If one substance condenses before the other, that means that its particles stick together more easily at that temperature. This result implies that the attractive forces between the particles are stronger in that substance. And this is how to dispose of your materials properly. This is task 2, sugar, salt, and oil melting points. These are the materials you will need: sugar, salt, cooking oil, a 1 tablespoon measure, cooking pan, stove, oven mitts or hot pads, timer, stopwatch, or clock. And of course, read this passage on lab safety before we do this. Keep all hair and clothing away from open flame. Be careful when handling hot objects to avoid burns. Handle cooking pans only by their heat-resistant handles. Use oven mitts or hot pads if the pan's handle isn't insulated. Observe the states of the salt, sugar, and cooking oil. At room temperature, sugar and salt are both solids. Oil is a liquid. What do the states of the substances tell you about their melting points? Sugar and salt are both solids at room temperature. Their melting points must be above room temperature. Oil is liquid, so its melting point must be below room temperature. What do the states at room temperature and the melting points tell you about the strengths of the forces between the particles for each of the 3 substances? Sugar and salt must have relatively high melting points. A high melting point means that a large amount of energy is required to separate the particles from each other. Salt and sugar must both have stronger forces holding their particles together than oil does. Part D. Next, you'll gradually apply heat to the sugar and observe the effects. Your goal is to identify the point at which sugar begins to melt. To get started, follow the steps and then answer the questions that follow. Pour 1 tablespoon of sugar into a cooking pan, spread it across the surface of the pan, place the pan on a stove. Because all stoves are different, you'll need to identify your low, medium, and high heat settings before proceeding to step 3. Use the method below to gradually heat the pan until you see the sugar begin to melt. Once the sugar melts, note how much time has elapsed and the final heat setting. If at any point the pan begins to smoke, immediately turn off the heat source and remove the pan from the heat. Heat the pan for these times and temperatures, stopping when the sugar begins to melt. 5 minutes on low heat, 5 minutes on medium-low heat, 5 minutes on medium heat, 5 minutes on medium-high heat, 5 minutes on high heat. When the sugar melts, turn off the stove, remove the pan from the heat. Don't touch the hot pan except by its handle. Use hot pads or oven mitts if the pan's handle isn't insulated. Let the pan sit off the heat on a heat-resistant surface until it cools. How many minutes did it take for the sugar to melt? It says in the example about 14 minutes, and the heat source was set to medium heat. Allow the pan to cool, carefully wash it with soapy water, place the used sugar in the trash or dissolve it with water and rinse it down the drain. If the pan is difficult to clean, let it soak in warm water for several minutes and then try again. Now we're going to do this process with salt instead of sugar. The salt didn't melt even when the heat source was set to high. There was no visible change in the salt throughout the heating process. Part F, room temperature is approximately 20 degrees Celsius for scientific purposes. A hot pan on a stove can reach temperatures up to about 260 degrees Celsius. What can you conclude about the melting points of sugar and salt? The melting point of sugar is somewhere between 20 degrees Celsius and 260 degrees Celsius. The melting point of salt is higher than 60 or 260 degrees Celsius. Consider the melting points of sugar and salt, as well as the states of sugar, salt, and oil at room temperature. What can you conclude about the attractive forces between particles in the three substances? Among these three substances, oil is a liquid at room temperature and has the lowest melting point. It has the weakest attractive forces between particles. Salt has the strongest forces between particles because it has the highest melting point of the three substances. Here is part H. Rank the three types of substances according to the strength of the forces between particles, weakest to strongest. Nonpolar, then polar, then ionic. And that is it for the unit activity and course activity for Unit 3. And those are scheduled for 11/19 and 12/02. So November 19th and December 2nd. So let me know if you have any more questions about that. And let's see if I can help you through those more. But until next time, have a good one. And I will see you guys and girls later. Bye-bye.